Okay, let's look at this one. We may have done it on the last video, but a good recap wouldn't hurt anyway, and if it's the first time, good enough. Let's say I've got this term here times this term here, and frankly, I don't need these parentheses. I did that just to keep everything in good order, just to make it easy on the eyes. So you multiply the 12 and the 7 and you get 84. You multiply the x to the 6th and the x to the 8th, and you add the exponents to do that, and you get x to the 14th. And radical 3x times radical 3x is just ordinary 3x. And all this is being times together. Now by commutativity and associativity and all that, you can do 84 times 3, you get 252. X to the 14th times x to the 1 is x to the 15th by adding of exponents. So there's that. So let's move on to the next example. 8 radical 3x minus 19 radical 3x. That's negative 11 radical 3x. Let's do this one. 8 radical 3x squared minus 19 radical 3x squared. You can go ahead and do the subtraction part first, but I like to do this part first. You see that x squared? 2 divided by this understood 2 is 1. X squared comes out as x. Again, we're assuming all variables are positive throughout this whole video from start to finish. So x squared comes out as x, and so we get 8x radical 3, and then minus 19x radical 3, and that's neg 11x radical 3. Or you could put the x on the back, but just be sure you don't put it inside the radical. That would not be good. So the only thing inside this radical here is the 3. Okay, so there's that. Now next, radical 27 minus radical 3. So let's see if we can combust this. 27, the biggest perfect square that will go into 27 is 9. And so we turn 27 into 9 times 3. And now we can't do anything with radical 3 right here. We just leave it be, copy and paste, for the time being anyway. Now, this 9 right here comes out as a 3 on the outside. So we get this 3 on the outside times the 3 that stayed in. This 3 right here had to stay in, so he just goes here. So we get 3 radical 3 minus 1 radical 3, because radical 3 is understood to be 1 radical 3. And so that's just 2 radical 3. Okay, so there's that. And let's look at this one. Radical 27 minus radical 75. We want to combust up into the biggest perfect square that will go into 27, and then do the same thing for 75 afterwards. So we turn 27 into 9 times 3, and as it turns out, 75 is 25 times 3, and 25 is the biggest perfect square that will cut 75. So again, we take this 9 out as a 3. On the other hand, the 25 comes out as a 5, and these 3's here and here stay in. So we get 3 radical 3 minus 5 radical 3, and that's negative 2 radical 3. And by radical, I mean square root. Okay. Now be careful about something. You remember, you can't fragment addition in general. The square root of 9 plus 16, that's the square root of 25, which is 5. Sure. However, notice that by order of operations, if everybody's inside, you do the adding first. However, with this, we got to take the square root first. You go ahead and take the square root of 9, which is 3. You take the square root of 16, which is 4, here, and then you add them at the very end, and you get 7. Notice here you get 5, but here you get 7. And that's because these are not the same thing. Remember, you can't break up addition. You can break up multiplication, like radical 9 times 16 would be rad 9 times rad 16, but that's not true for addition, as we see here. We get 2 different things. And just out of curiosity, let's do it already. So, like the radical of 9 times 16, well, 9 times 16, that's 144, but the square root of 144 is 12. Now, and let me come inside, and now if you break it up, you should get the same thing, because multiplication is nice. It's breakup-wise, it's nice. So let's make sure that happens. The square root of 9 is 3, the square root of 16 is 4, and yep, there's 12. So with multiplication, as long as everybody's positive, and we are well, there's no variables here anyway that are negative, so everybody is positive, so we can break this up like this, and we're good to go. All the numbers are positive, I should say. Okay. Now be careful. Radical 27 minus radical 26, that's 3 radical 3 minus radical 26. We can turn that 27 into 3 radical 3. You just go through the same steps here, that 9 times 3 business. But you can't do, after that though, you can't do anything else. Notice at radical 26, it won't break anymore. And even if it did break some more, that wouldn't necessarily mean they're compatible, even if it did. So, but point being, we can't go any further. This is as far as we can go. And, well, oops, I didn't know I'd already done that down here, but oh well. So here I'm illustrating again that as long as everybody's positive, the radical of the product is a product of the radicals. That's the way of putting that, okay? And so I guess that rendered this guy up here unnecessary, but oh well. Now, there is one thing I'm not going to totally avoid negatives the whole time. If I stick a negative outside the radical, that's fine. The negative of radical 16 is negative 4. You're just multiplying the square root of 16 by neg 1, and you're getting negative 4. However, if you try to take the square root of negative 16, you can't do it in the reals. You can get later on, we'll get a thing called the imaginary number. You'll get like 4i, 4 times I, but we're not ready to go there. For now, let's just pretend like we can't do this. It would take us out, in the real numbers, we truly can't do this. You can extend to the complex numbers and do it, but I don't want to go there right now. So the square root of negative 16 is not the same thing as the negative square root of 16. And in fact, you can't do it in the reals. You get an imaginary number out of it, for this guy right here, that is. Okay, and watch out about something, students, like the negative of 5 squared is negative 25 because the negative is not being involved in the squaring. You're doing negative 1 times the square of 5. But here, you're doing the square, if you put parentheses around everything like this, you really are squaring negative 5, and you're doing negative 5 times negative 5, which is positive 25. So be sure to distinguish between this and this. Okay? Now, radical 5 squared, be careful about something like radical 5 squared, that's going to be 5. And radical negative 5 squared, that's going to be 5. Be careful. The cancellation laws with that's why I avoid negatives as well. Things get a little shaky. Like if you square neg 5, you'd get pos 25. But if you just take the principal square root of 25, you get positive 5. You don't return back to negative 5 here. And you can sort of, at least, you might could see why I'm going to stay positive as much as I can. Now, be careful. Now, this guy right here, this is negative 25 in here, and we'd get the square root of negative 25, and we'd have to use the imaginary numbers. So this is not real. And here's it now. Again, you can use 2 or you can do 4. You get 6 in return. Now, this is, for even roots, this happens to us. Like this guy right here would give me 6. Either one of these guys would give me 6. For odd roots, this isn't really the case. For odd, well, it's actually even nicer. For odd roots, it preserves, it's okay to put a negative number in an odd root. It's not okay to put one in an even root. But this isn't really a negative number. This is a positive number, really, because this is negative 6 quantity to the 4th power is some positive number like 2196 positive. So this isn't really negative here anyway. We can't do this one though, because this really would be negative. Now, the cube root of pi cubed is just pi. The cube root and the cube, remember, you do 3 divided by 3 and get 1. In other words, the cube root and the cube, they self-destruct, and they just leave you just the bare naked number, which is pi in this case. But anyway, the nth root of x to the n is just plain x, as long as we're assuming x is positive, okay? Greater than 0. For odd roots, we can actually be lenient, and we can let x be equal 0 or be less than 0. I didn't really put the equal to part here, but oh well. It's actually good for equal to as well. Now, if n is even, we must have x positive for it to hold true. And really, I could put or 0. But, guys, let's not mess with 0 too much. Let's just assume that x is strictly positive. This whole time I've been assuming strictly positive, as in strictly greater than 0 throughout all these videos. So let's keep assuming that for the time being, okay? Let's keep assuming strictly positive, meaning you're not negative and you're not 0. You are assume we're just positive. We're strictly above 0, or to the right of 0, whatever way you'd rather look at it. Now, it is worth pointing out the cube root of negative 125 is negative 5. You know, we're not doing variables here. Whereas the cube root of a negative, and you'll just get another negative back. After all, negative 5 times negative 5 times negative 5 is negative 125, okay? the fourth root of 625 is 5, but you can't do the fourth root of negative 625 in the reals. You would actually have to use some fancy complex number stuff to do that. That would even go beyond the scope of Algebra 2, I think. You'd have to, yeah, you'd almost need some trig stuff to do that, I think. De Moivre and all that. Let's not go there. Now, you can do the odd root of a negative. Like the fifth root of a negative, you just suck out the negative. And then, so you get a negative, and then do the fifth root of 32, and you get 2. You do the fifth root of 243, and you get 3. So we got negative 2/3. You just do the fifth root of the top, the fifth root of the bottom, and off you go. And watch out, let's see, the fifth root of neg 13 to the fifth. Like here, with odd roots, you know, the 5 and the 5, they just destroy, and you get negative 13. But now with the fourth root, you get the absolute value. You only get the positive version, because this the fourth power kills this negative here. So even roots are much more persnickety about negatives than odd roots are. It's okay. Now without the parentheses, watch out for a different reason. Now this one is still fine. This and this are actually the same. This parenthesis really didn't even matter since it's an odd root and odd power. In particular, just since it's an odd power. But however, notice here, we're doing the negative of 13 to the fourth. This would be a negative number in here, but in the reals, we can't do the even root of a negative number. So in the reals, the moral of the story, we can't do an even root of a negative number. Okay. Like here, the cube root of negative 1 over 64, just yank out the negative. The cube root of 1 is 1 itself. The cube root of 64 is 4. And again, the cube root of neg 64. Now, if we did the cube root of neg 64, that'd be negative 4. Okay. After all, negative 4 times negative 4 times negative 4 is negative 64. Like the square root of 80, the biggest perfect, since we're doing the square root, we need to look for a perfect square. 16 would be that perfect square, the biggest one that would cut 80. So that's the square root of 16 times 5. So you can just break that. Some students just skip this step right here, but I went through it in this time. In this case, I don't always do this step. But that's radical 16 times radical 5 by the multiplicative breakup rule. But the square root of 16 is just 4, so it's 4 times radical 5, or just 4 radical 5 there. And by radical, I mean square root. Okay. If I do another one, radical 80 minus radical 245, that's, again, breakup 80 is 16 times 5. Breakup 245, you can kind of tell that 5 will go into 245. Divide it out and see what happens, and you'll get 49 times 5. Aha. 40. And then you can tell that 49 will be the biggest perfect square that cuts 245, or cuts into it. Now we can take out the 16 as a 4, take out the 49 as a 7, we're doing square roots. So that's 4 radical 5 minus 7 radical 5, and that's a neg 3 radical 5. Okay. And then, let's see. And if you just stick x's inside, you can do the breakup rule again. The biggest perfect square that cuts 80x is 16. And really, this times sign here is kind of, you can keep it, but it's really superfluous. You could just say 16 times 5x and then break it up. That's radical 16 times radical 5x. And then that's just 4 radical 5x. And note there's an x in there this time. Now, if I stick in an x squared, well, now here's the thing. I tell you what would be almost a better idea. X squared is going to come out as x. We're assuming x is positive, of course, as always. So we break this up as radical 16 times radical 5 times radical x squared, and by commutativity and all that, you'd get 4 times rad 5 times x, but it's cleaner to write that as 4x radical 5, okay, just by commutativity and all that. It's just nice and clean to have that radical on the very right side. It's not that we have to, it's just nice. I tell you what would almost been more economical. If I would have, you can leave it like that, or you can just say, look, we're doing 16x squared times 5, and then excuse me, let me go inside. Just keep the 16x squared together. Since they're both perfect squares anyway, there's no point in breaking them apart. I mean, you can, but it just leaves you with more to do at the end anyway. So there we go. And that 16 comes out as a 4, and x squared, you divide this 2 here by this understood 2 here, and you get 1, so it's x to the 1. So it's just 4x radical 5. And for 80x cubed, Again, you want to break off x cubed as x squared, or as x times x squared, I mean. So you got 16 times 5 times x squared, and you can break this all up like this. Now, 16, radical 16 is 4. Radical x squared is x itself. And so we get 4x. Now, this radical 5 times radical x, it comes back together as radical 5x. Okay. And to be honest, this is not the most economical way of doing this problem. This is correct, but I tell you what's more economical. Well, if it'll let me do it. And that's excuse me, I need to get rid of, let me get rid of this. So 16, just keep the 16 and x squared together. It's sort of like I did on the last problem in its own little way. And I need to get rid of this now. And there's no point in splitting the 5 and the x apart. And you can just take the square root of 16x squared, that's 4x, and then times radical 5x. The times sign is understood over here. So there's that. And again, now for x to the 4th, again, I didn't really do it the economical way. That's just going to be 4 times rad 5 times, but that's x squared. You remember, you do this 4 here, divided by this understood 2 here, and you get 2 right here. So you get 4x squared times radical 5. And if you want to be economical, you can do to this x to the 4th what I did to the x squared up here. But, I made a mistake up here. There should be an x right there. Sorry. My bad. I forgot my x up here. So, but anyway, you could do this x to the 4th, what I did to this x squared up here, and just go to town. And then likewise, let's use something less pedestrian, like 24. Then what you can do is you can split it apart again. Radical 16 is 4. Now, again, you do 24 divided by 2, and that's 12. So it's 4x to the 12th times radical 5. And you can do that more economically, just like before. Now, what if I do something like 25? You break it up. Really, it would have been more economical to keep my x to the 24th right here beside the 16, which I could have done, but anyway. This is fine what I did here. So I got 16 times, the biggest perfect square that cuts 80 is 16, so 16 times 5. Now, I want a multiple of 2, which is just an even number, in other words. So I turned 25 into 24 plus 1. And so I got radical 16. Now that 5x, since neither one can come out, there's no point in splitting them apart. And really, to be frank, I could have just as well kept x to the 24th in here with the 16, but oh well. So radical 16 is 4. 24 divided by 2 is x to the 12th, and then times radical 5x. Guys, if it helps your feelings any, what I could just do is just put x to the 24th right here. And just go over here and just get economical with it. Let's get economical. Let's keep 5x together, and let's keep x. This is all the same stuff, but I just wrote it in a much more economical way. What I did before was correct. I just wanted to go economical. Okay, so there's that. And I'm assuming, as always, all variables are positive, all that. And for this one, the 4th root of 80. Now this time, be careful. I'm not doing a square root anymore. I'm doing a 4th root. So I need the biggest 4th power. As it turns out, 16 has a beautiful benefit. He's not only a perfect square, he's a perfect 4th power. That's pretty rare for a number, but 16 satisfies it. So 16 it is again. But now the biggest multiple of 4 that is below 27 is 24. So I break up 27 into 24 plus 3. So x to the 24th here, x to the 3 here. And I put the 16 and the x to the 24th together because they're perfect squares. And I put the 5 and the x cubed together because they're not. Notice this is all multiplication. It's 16 times x to the 24th times 5 times x cubed. But anyway, the 16 comes out as a 2 because I'm not doing the square root, I'm doing the 4th root of 16. And I do 24 divided by 4, which is 6. And then times the 4th root of the stuff that could not come out. And there's that. So I'll stop the video here. I'm out of time. Thank you. I'll see you on the next video.